Okay, let's get started with this session. It's my great pleasure to introduce Alex Dimakis, who is the co-director of IFML and for a long time was a colleague and professor of mine at UT Austin. And it was a very dark day when he left and decided to move to UC Berkeley. But I know that he is thriving there. He's a world expert, started off in coding theory and information theory, signal processing, and is now a world expert in deep learning for image analysis for inverse problems, and is now one of the leaders in open sourcing AI. He has a startup at the same time, Bespoke Labs, and he's here to talk to you about all of these things today. He's also one of the best people to give a talk and one of the most entertaining speakers that I know, so I'm sure he won't disappoint you. So thanks for coming, Alex. Thanks.
Thank you. Thank you very much. Let's see. Okay, it works. So I'll be talking about data curation for agents. Okay, the first point that I think we all agree is that data sets are the foundation of progress, or one of the most important foundations of progress. And we all understand that previous data sets like MNIST and ImageNet had a tremendous impact in scientific progress. A few years back, we realized with Ludwig Schmidt that one of the most important data sets, the web image text data set that was used by OpenAI to train CLIP, was not open, unlike all the other data sets that I have on this slide, which is MNIST, CIFAR10, and ImageNet. So we're like, oh, we have to actually get serious into data curation that creates open data sets. So we started this sequence of projects that are called DataComp for data competitions. And the first version of it, the first paper was called just DataComp, and it was basically creating a multimodal data set. The data set in that case was images and captions describing those images, and it was at the billion image caption scale. So we created it by scraping the web, cleaning up things, having other models that were filtering for quality, and so on. And that was finally published in NeurIPS 2023. And it has had a significant impact because several other models like OpenClip and Stable Diffusion 3 are using the DataComp dataset. And overall, we find that creating high-quality data sets is a way to have big impact both in industry and in academia, and it kind of has a lasting value. So the second version was called DataComp for language models, DCLM. And DCLM is basically a pre-training data set. So pre-training means basically high-quality text, raw text, which we started from Common Crawl, which is a scrape of the web. And we ran several filters for quality, for language, for content. And there's a whole detailed data curation process there. And also we trained LLMs to verify indeed that our data set was very high quality. So the paper has hundreds of experiments where we train hundreds of LLMs at different scales, and we show how different ways of filtering text data affects the quality. So that was a NeurIPS 2024 paper. And this is the DCLM team, and you can see that has a very large, it consists of many, many students. And I want to give full credit to the students who did an enormous amount of effort, including a lot of engineering, to create the DCLM data set. Then the next version of this was on post-training. Now, on post-training and reasoning, the data set is not just raw text, but rather it is questions and answers. And the answers have to have detailed reasoning traces that involve backtracking, reflection, and all the things that stabilize basically the reasoning process for LLMs. So in this version 3 of DataComp, which we called Open Thoughts, we curated a very high quality reasoning data set of 1 million questions and answers. And the way we created that, again, by starting from the web, we found various sources of questions in math, science, and coding. And then we had many LLMs filter out which were the higher quality questions. There's a whole section of deciding how to decide what questions to keep or rewrite with other LLMs. And then we answered them with different LLMs, which were reasoning. And that way we created the data set that's called Open Thoughts. And we also trained models that are called open thinker models at 3B and 8B and 32B. And then we evaluated how those models were performing compared to DeepSeek, R1, and the other reasoning models. And our goal was to create a reasoning model that also has open data and a full open recipe and full open code. So DeepSeek R1, as you may know, has open weights, but it doesn't have open data. Whereas OpenThinker has open weights and open data and a full process that you can replicate the whole process end to end. And it actually outperformed DeepSeek R1 at the A7B and the 32B scale. So that was kind of the big effort we had there on the reasoning. And since then, the reasoning data sets that we created have been used very widely. This is the Open Thoughts team. Then again, you can see the composition of the students, and also there's many universities involved. IFML has been instrumental in all the data competitions by funding many of the students, providing the compute, and supporting in many ways. So it's definitely clear that none of the data comp projects would have been possible without IFML. And here's just some examples of impact that Open Thoughts have had. There is, I think, dozens of models that have been distilled from Open Thinker models. Frontier labs, including Microsoft, Meta, AI2, and so on, are using both our data set, Open Thoughts, and our models. And you can see, for example, that the Open Thinker model has been downloaded, I think, 600,000 times now on Olama. So there's a lot of people who just download the models for various reasons, including to just have them to chat locally. So that was the Open Thoughts project. And the thing I want to tell you today is the last version, the one that I'm the most excited about, which is version 4 of Datacomp, which is Datacomp for agents. And this project is starting now, and I'm super excited about it. So I want to tell you what we're doing and why I think it can be very interesting. So for agents, so we call it Datacom for agents, but the other, if you ask me, okay, how do we evaluate agents? My preferred platform is what's called Terminal Bench, which is another paper we recently wrote. So I'll be telling you about how Terminal Bench is, I think, an exciting platform to develop and evaluate agents, and what we're doing with Datacom for agents. So the first question is, okay, what is an agent? And before we get into that, what is an LLM? So an LLM is a box that takes tokens and produces tokens, right? So you can put some text input and you get some text output. For example, you say, I like to eat apples and you get bananas out. Now, the important thing here is that an LLM cannot do a Google search. It cannot move your files. It cannot send emails. It cannot book a trip to Hawaii. It cannot send your data to China. It cannot do any of those things, right? So an LLM is just a machine that takes tokens and produces tokens. To perform inference on an LLM, you have to either run it locally by using, for example, VLLM or Llama, or one of the other inference softwares, or you call it by an API. So if that's a hosted LLM that's in OpenAI, then of course you're sending your data to OpenAI. But if you download DeepSeek R1 and you run it locally, then you're not sending your data anywhere, right? So it's important to know this. Now, the next thing here is that sometimes the LLM can produce tokens, text, that looks like this curl command that I'm showing you here. Now, the LLM cannot execute any command, right? Because all it does is spits out tokens, words. But you can make another Python program afterwards that looks at these words and executes them as a command, okay? So this is called an LLM with tool use. So you can ask yourself, is an LLM with tool use an agent? And my answer is no. An LLM with tool use is just an LLM with tool use. That's not what I call an agent, okay? And then you can ask yourself, okay, let's say I have a question that requires additional information. If you go to ChatGPT and you say, what is Alex's email? It should tell you which Alex are you talking about, right? So what people said is, all right, I will have this database of information and I will have a retrieval mechanism that takes a query, like what is Alex's email, and performs a search in this knowledge base or this database, and it retrieves back a bunch of text chunks that hopefully contain the answer to the question, what is Alex's email? And then after it takes all those paragraphs of text, it adds them in a big prompt. So it does this prompt construction process that says, okay, GPT, some user is asking what is Alex's email. Here is a bunch of paragraphs that I found in the database that hopefully contain the answer to this question. Can you do your best to answer the question given the retrieved text? And then you feed this into an LLM, and the LLM produces an answer. Is this an agent? So my answer to that is no. This is good old RAG, retrieval augmented generation, where you just have basically a single tool use. So there's a tool that is the retrieval mechanism. And then after you have the retrieval, you construct a prompt with a hard-coded Python script, and then you call the LLM once. So this is basically a hard-coded LLM workflow that involves a single tool call and then an LLM call, right? So that's not an agent. And then you can have a slightly more complicated situation where the user asks a question and you have an LLM call that decides, does this user want to change their password or do they want to install a printer, right? So then there is a second LLM call that says if they want to install a printer, you go to this workflow. If they want to change their password, you go to that workflow. So think of this as basically a bunch of LLM calls and then a sequence of hard-coded Python programs that are executed on a tree. So many people call this an agent, okay? And again, I would like to say this is not an agent. I would call this just a workflow. And there's many softwares like LangGraph and LangChain and Microsoft agentic tools or graphical user interfaces that will allow you to draw little boxes and write little prompts and construct an agent like that. But in my definition, that's not really an agent. By the way, if you're a company, you don't have to worry about this, in this audience, but many companies are trying to sell workflows as agents. And I understand the marketing department has to call them agents. And I'm like, okay, fine, call it an agent if you must. But the real definition of an agent from a research point of view is something that has an extra crucial component. And this is basically what's happening. A user asks a question, it goes through an LLM, and then the LLM thinks, and then it decides to execute some commands. And those commands can be move some files or write some Python or call a web search or, do something with a credit card, book a flight. And then it sees the response of the environment, the state of the world, which can be the terminal screen or what the browser responds back. And then it takes all this, it summarizes it again. It usually compresses it because if it takes multiple actions, this sequence of events can become extremely long. So it must have a memory mechanism or a summarizing mechanism, some attention to remember what it has achieved versus what it needs to do. And this whole thing is running in a loop, okay? So that's the key thing. So agents are LLMs in a loop. And there is, that's called a react loop sometimes by reason and act, is truncated in this classical paper. It's called react. So that's what an agent is to me, something that is an LLM in a loop with all these mechanisms for memory and planning. So people right now are making agents by basically constructing prompts. And because the prompts were becoming very long and they were unstable, they were splitting a prompt into multiple prompts, and they were calling this multi-agent system. And a multi-agent system is basically a multi-prompt system. And it's very unstable, basically. This is called the long horizon problem, that agents can do 3 to 4 to 5 things, but the moment they make a mistake, they have no way of recovery. And if you have 90% chance of doing the correct thing, but you have to do k things, you have 90% to the power k to execute everything correctly. So inevitably, the moment your agent has to do 10 or 20 or 30 actions, or executing something that a human would take an hour or a day or a week to do, that inevitably, unless you know how to recover, you're going to fall off the cliff, even if you make your reliability per step to be 99,999. It doesn't matter because your number of steps is actually scaling. So the only way to stabilize agents is to have them try to solve tasks by themselves, see how they fail in a real environment, and do reinforcement learning so that they can recover from their own mistakes. So you have to build environments. This is a very interesting paper that appeared recently that analyzes how LLM multi-agent systems fail. And it basically, I think, says that, yes, you can make simple workflows with 2, 3, 4 steps, but the moment you try to make an agent that analyzes data sets or writes Python or fixes real repos, you have to do something else, as Claude Code and deep research agents are doing. So we're moving from LLMs, where you study what does an AI system know, right? And to the left, you see this paper, the MMLU paper, that has had tremendous impact. And it's basically testing, it's asking LLMs questions and it sees what they respond. But in agents, they don't care about what they know, they care about what they can do. So in order for them to be able to do stuff, you have to give them a computer. You have to give them a browser, you have to give them a terminal, you have to give them Python and so on. So the whole game of Terminal Bench is constructing software that allows agents to safely execute Python and Bash commands and move files and call the browser and so on. So you may have heard of, how many people here have heard of Claude Code or Codex? Okay, great. Claude Code is an agent that controls your computer. It can move files, it can write Python and so on. So this is, I think, where the frontier is right now. And this is a tweet that says basically CLI, command line agents, are an extremely powerful paradigm for performing things beyond just asking an LLM questions, but rather giving it files and so on. So Terminal Bench is exactly a framework for allowing the open source community and researchers to create agents that control the command line interface. So a Docker container, which is a virtual machine, you give that virtual machine to the agent, and you just make sure that inside this Docker container, there are all the files needed so that a task can be performed. You give it a terminal. The agent literally can type keystrokes and observe back the screen. And the framework is a whole execution engine that allows you to run agents very easily like that. And then there is a benchmark that has 80 handcrafted tasks created by PhD students and researchers, which will test the agent in all kinds of diverse tasks, including data science tasks, data analysis, scientific computing, biological tasks, and so on. So this is kind of the key architecture of Terminal Bench. You start in a Docker container. There is the terminal. The agent is a Python file that's called terminus, for example. And the agent is calling any LLM by API. But the important conceptual difference is the agent is not the LLM. The agent is something that's running locally, and it types keys on your keyboard. It sees the screen, it summarizes the screen, and then it can do as many LLM calls as it wants. So there's a separation between the agent, which is terminus.py, which has memory management, tools, and so on, versus the LLM calls. So I think this is an important paradigm change. And this is exactly created to evaluate Claude Code or Codex, because you can literally put Codex in there and it will be exactly solving tasks. But it's an environment to evaluate and train Claude Code or Codex and these command line agents. And when you create an environment, you don't only have to give the task, you have to describe all the files, and you have to set up this container to be exactly as the problem was when the things got problematic. So a task or a data set consists of three things: task descriptions. For example, I'll describe this with a specific task. The specific task is when you break pip or when you break conda or you break Python, like the dependencies are not working. I don't know if you have been in this dependency hell, but this is a big problem that many of us spend hours dealing with. So I will set up a Docker container that has a broken pip. So the agent wakes up in this container and the task is my Python is broken, fix it. The setup of the container is a Docker setup file that breaks this. And the crucial other thing is there's a verifier in there. There's some test scripts that will verify that after the agent says I'm done, you will truly be able to actually run Python packages again. So this is an example of a task. And this is where this task is. This is open source. You can find the task. And the task has the Docker file, which installs Python and breaks it. The task.yaml, which says my Python is broken. And the tests that verify that the agent has fixed the problem. And we created 80 of those. and we tested all the agents that are out there and see how well they do. So you can see many other tasks here, as I said, ranging from scientific computing, DNA problems, any problem you can think of that runs in command line. Basically, if your student can do something using a computer with command line, you can package it as a terminal bench task and contribute to the benchmark, and please do, because it's all open source and we do need more contributions. And I have many examples here of different tasks, from run this Python analysis to, break this code or fix this broken SQL tables and so on. Now, the impact of Terminal Bench is that all the frontier labs have picked it up and they're using it as the de facto standard for evaluating terminal agents. So when Claude 4 was announced, they reported two benchmarks, Swim Bench and Terminal Bench. So Claude Code is I think, at 55 or now, so it has improved a little bit since the announcement. But the point is that the frontier labs care a lot about evaluating on Terminal Bench, and we are creating new versions of Terminal Bench with new tasks, and we invite the open source and scientific community to contribute more tasks so that we can keep evaluating real agents in real setups. This is kind of the scoring of the latest models, and you can see there's still a lot of headroom. So GPT-5, even with the best harness, has a long way to go. So the benchmark is not saturated, and that's very important. So conclusions to wrap up, Datacom projects always create data sets, and the first one was on CLIP, the second one was on pre-training, Open Thoughts was on post-training, and now we're creating a Datacom for agents, specifically a Datacom for terminal bench tasks. Agents, as I said, are LLMs in a loop, deciding what to do next. And it's very challenging to make agents stable unless you actually allow them to run themselves in real environments. And I think that's the most important point. So the evaluation of agents requires the setup of environments and verifiers so that you can truly let them run and measure performance and get gradients to do your reinforcement learning. The first step to optimize them is prompt optimization techniques, like a recent paper we have that's called JEPA. I think that goes a surprisingly long way. But beyond prompts, you have to make better tools, like give them better memory management or actually do post-training with SFT and RL. And Terminal Bench, for example, has incorporated the SkyRL platform to do reinforcement learning. And it's a very easy way. If you want to run RL now on your agent, you can use SkyRL in Terminal Bench. In general, data in the world of agents is now replaced by environments. So it's not just a question and an answer. It is a question and a verifier, which checks the answer, and a Docker container that describes the state of the world when the question is asked, okay? And I think this is a huge paradigm shift when we're going from answering questions to having agents that will be able to do things. So I'll stop here, and I want to invite everyone to, if you want to contribute to Terminal Bench by tasks, I'm very happy to discuss more after this or offline. So thank you all very much.
Great talk, Alex. Any questions?
Yes, thank you for your talk. I was very curious, when you have these verifiers, do you just verify that the problem is fixed, or do you also verify that nothing else was messed up in the meantime?
So creating the verifier can be very challenging, and we have spent sometimes many days, like we have spent possibly 100 hours on one problem, because the problem can be solve this. So here's a bunch of Python files, fix this bug. So you can write tests, but you have to make sure that you didn't break anything else, and you also have to make sure that the agent is not reward hacking. So reward hacking means that the agent is exactly like a student that tries to cheat. Okay, so for example, is our buttons being pressed? Okay, I'm not doing this. Okay, reward hacking is, imagine you give an exam, but you have a solutions file. The agent, if the solutions file is in the Docker, the agent will literally find the solution file and copy the answers and cheat. So you have to make sure that you package the Docker container in a way that all the tests are hidden, and there is no hacky way that the agent can get full reward, because if it can, it will. So a lot of our effort goes into making AI tools that observe the trajectories and make sure the tasks do not allow reward hacking. Because if you have tasks that allow reward hacking and they get into the training loop for any agent, the agent, like a real human, will learn that cheating is rewarding, and they will try to cheat out of anything. So it's actually, it's like, we're building an education system for our agents, right? And yes, we spend an enormous amount of time making sure that the trajectories are truly solving the problem.
Get to you in a second. Quick question.
Thank you very much to give us the new concept of agent, because before the multi-agent, agent actually just a different role playing. You just give different role that agent play. So we actually did a test actually for many multi-agent system. Single agent is enough to run the same task and achieve roughly the same result. So that in the current domain, like multi-agent system is like not you say the LM has to be in the loop in the thing, right? It's most just different role playing. And so do you think in the future we do have like a multi-agent system, like so how your system actually, for, I mean, healthcare, so the people use LM for different role, like you're different doctor in cardiologist, in oncologist, they actually are different role. They're discussed about the use case to do the triage. So how yours multi-agent system, and here in my area, the multi-system are like similar or different? How you think this, in the future, maybe many multi-agent system will disappear, actually one single agent actually can do all these roles?
Yeah, so multi-agent was just an easy way to create an agent by writing multiple prompts as opposed to a single prompt, right? Because when the only tool people had was writing prompts, and they tried with one big prompt, they said, okay, that breaks. Let me break the problem up into 5 sub-problems and create a prompt for each problem. Now, I have no, like, if this works for a specific workflow, that's great. That's the easiest way to go forward. Where it stops working is when you have complicated tasks that require many steps. So, but even if you want to make a multi-agent system, you should still run it in terminal bench to make sure that your agent, or just basically run it, is my zeroth order recommendation, is don't just run it once and ship it. Just make sure you have a real evaluation where you can measure what % of the time your agent truly solves the tasks that you want it to solve. So the evaluation is if there's one message here is you can't just write some prompts and ship the thing and hope for the best, because it's a disaster. And many people have seen this. You have to evaluate your agent in real environments. And that's what terminal bench is. It's basically a very easy way to evaluate any agent. And you can make your agent in LangGraph and evaluate it in terminal bench, yes.
This is great stuff. Thank you so much for doing this. When you're testing new systems, new ML systems, you often test them for generalization out of distribution. Do you have a way of assessing out of environment for these kind of benchmarks?
How do we not overfit, you say? Yeah, so what we're planning to do in terminal bench is we plan to release a new benchmark every 6 months to a year. So there's going to be a terminal bench 2.0 and a terminal bench 3.0. So yes, you can, if you want, you can take the existing problems we have released and hire experts to solve them, and then SFT on the solutions, effectively cheating. You can do that, and you will be high on the leaderboard, but in 6 months you will be on the 0 on the leaderboard, and somebody will tweet that, and that's not going to be good stuff, right? So that's the way you maintain the value of a benchmark, in my opinion, is it has to be a live benchmark. So a new version comes out every 6 months, and people who cheat are penalized.
Thank you for the great work, and I think in this domain you have an advantage of relatively more well-established infrastructure for the terminal bench or also CS stuff. And when we're applying similar idea of applying language models to other domains, especially involving wet experiments, for instance, chemistry, material, and bio, we're facing the data problem. So we have different ideas, but we kind of face a challenge here. So if we use the existing corpora, it's kind of static and it's not directing to the unknown knowledge that we want language models to explore. If we use want to use the reinforcement learning with like experiments signal in the loop, the speed is very slow, so it's not matching the RL needed for training language models in CS domain or math reasoning. If we use, we also thought about using. Yeah. So any question, any suggestions on the like what kind of data, like how to speed up, how to apply these ideas to the other experiment, like scientific domains?
Yeah, I've been thinking a lot about this. If you can package a task as a software task that involves just a set of files and some tests that correctly verify if the problem was solved. Like, for example, protein folding or anything like that can be easily packaged as a terminal bench problem, because you describe the sequence and then you have the ground truth structure, and you can run a script that sees how well the predicted structure matches the true structure, right? So anything like that you can package as a terminal bench problem. And the agent now can write Python, or if you want your agent to use custom tools, you just have to upload those tools in the Docker container and describe how those tools work to the agent. So I'm basically truly interested in expanding the terminal bench benchmark by adding, chemistry, science, biology tasks in there. Now, if it involves human experimentation or robotics experimentation, that's out of the context of this problem. It's a much harder problem. So for that, I don't have anything interesting to say, other than, of course, we have to keep studying this. Yeah.
We are out of time,
Great.
but so let's thank Alex again.